For each polynomial function, 1. Find the zeros and their multiplicities. 2. Find the y-intercept. 3. Describe the end behavior. And 4. What other points are required to draw the graph accurately? Use this information to sketch the graph. In part A, we'll graph p of x equals -1 times 2x minus 1 times 2x plus 1, a quadratic polynomial with a negative leading coefficient. We'll begin by finding the zeros and their multiplicities. We can find the zeros of the polynomial by solving p of x equals 0. This is represented by the equation -1 times 2x minus 1 times 2x plus 1 equals 0. Set each factor equal to 0 and solve for x. (2x minus 1 equals 0 when x equals 1 over 2). (2x plus 1 equals 0 when x equals -1 over 2). The x-intercepts are -0.5 and 0.5. Next, we'll find the y-intercept. At the y-intercept, x equals 0. Evaluate p at 0 to get the y-intercept. When we plug in 0 for the function input, we get a result of 1. The y-intercept is located at the point 0, 1. Next, we'll describe the end behavior. We have a quadratic polynomial with a negative leading coefficient. The trendline for this graph will match an upside-down parabola. We can sketch the graph at the x-intercepts by considering the trendline and the multiplicity of the zeros. What other points are required to draw the graph accurately? We know this is a parabola, so let's find the coordinates of the vertex. In a parabola, the vertex can be found on the axis of symmetry. In this graph, the axis of symmetry is the line x equals 0. As it turns out, we already found this point when we calculated the y-intercept. We now have enough data to draw the graph. In part B, we'll draw the graph of p of x equals x times 4x minus 3 times 3x plus 2, a cubic polynomial with a positive leading coefficient. We'll begin by finding the zeros and their multiplicities. We can find the zeros of the polynomial by solving p of x equals 0. This is represented by the equation x times 4x minus 3 times 3x plus 2 equals 0. Set each factor equal to 0 and solve for x. The first factor, x, becomes 0 when x equals 0. For x minus 3 equals 0 when x equals 3 over 4. (3x plus 2 equals 0 when x equals -2 over 3. The x-intercepts are -0.67, 0, and 0.75. Next, we'll find the y-intercept. At the y-intercept, x equals 0. Evaluate p at 0 to get the y-intercept. When we plug in 0 for the function input, we get a result of 0. The y-intercept is located at the point 0, 0. We already have a point there from when we found the x-intercepts, so there's no need to draw a second point. Next, we'll describe the end behavior. We have a cubic polynomial with a positive leading coefficient. The trend line for this graph is y equals x. We can sketch the graph at the x-intercepts by considering the trend line and the multiplicity of the zeros. What other points are required to draw the graph accurately? We should get 4 more points. The first point we'll get is to the left of the first x-intercept. Let's get the point where x equals -1. When we evaluate p at -1, the result is -7. We have a point on the graph at -1, -7. The next point we'll find is between the first two x-intercepts. We know the graph rises above the x-axis between -0.67 and 0, but we don't know the relative maximum. Use the maximum feature of your graphing calculator to locate the relative maximum, -0.3814, 1.4772. The next point we'll find is between the last two x-intercepts. We know the graph falls below the x-axis between 0 and 0.75, but we don't know the relative minimum. Use the minimum feature of your graphing calculator to locate the relative minimum, 0.4370, -1.8115. The final point we'll find is to the right of the last x-intercept. Let's get the point where x equals 1. When we evaluate p at 1, the result is 5. We have a point on the graph at 1, 5. We now have enough data to draw the graph.